General relativity, step by step. I'm going to talk about the Jacobian. There's a very nice Wikipedia page, which is here. I talked about it. The reason I'm doing it, rather than just directing you to the page, is to show you that what kind of notation I want to do. And I'm going to give what notation I'm going to use. And I'm also going to slant it towards coordinate transformations. So last time we talked about f of x comma y, just a scalar function. Now I'm going to talk about vector functions. So I might have f equals f of x comma y and g equals g of x comma y. So we've got two vectors. We've got x comma y is mapped to the vector f comma g, where each one of these guys, f and g, depend upon x and y. And I'm just going to write the Jacobian down. I say Jacobian, but I never know if it should be, because it's Jacobi, so Jacobian perhaps. But everyone I know says Jacobian. Maybe I should try and say Jacobian. Die f, die x, die f, die y, die g, die x, die g, die y. That's just what the Jacobian is. It's every possible, and of course you can see how to generalize it to more than two variables, but it's every possible way of calculating all the partial differentials that you can with this functional relationship here. It doesn't mean very much without an example, so I'm just going to give you a nice example. I'm going to convert between Cartesian coordinates and polar coordinates. I'm going to make heavy use of this as an example. I'm also going to generalize it in different ways, so we'll see how it works. So instead of f and g, I've got r and theta. R equals the square root of x squared plus y squared, and theta equals arc tan of y over x. So what I really mean is that r squared equals x squared plus y squared, and of course tan theta equals x over y. So it doesn't hurt to draw a little diagram. X and y, there's my little point, that's distance r, theta, x comma y is defined in terms of polar coordinates r and theta with these relationships here. So let me just work out what my Jacobian is. Well, here when I wrote down the definition we had f's and g's, and now I've got r's and thetas. So it's die r, die x, die r, die y. Is that how I did it? Yep. Some people, of course, define it as the transpose of what I've got here. Die x, die theta, die y. So when you say Jacobian, some people mean the matrix determinant of this matrix here, but I'm going to reserve Jacobian for the actual matrix. J equals. Right, and then we just whack in the terms. I'll just pinch in a little bit. Die r, die x. Well, that's just differentiating this thing here. So that's x over root x squared plus y squared. Calculus. Remember, it's partial differential, so we hold y constant. And by symmetry, this one's easy as well. That's just y over root x squared plus y squared. Now what have we got? We've got die theta by die x. Here it is. So the differential of arc tan is 1 over 1 plus x squared, and that's arc tan y x to the minus 1, isn't it? So when we differentiate with respect to x, we get minus y x to the minus 2 over 1 plus y over x all squared. And this one here is die theta die y. Die theta die y is 1 over x over 1 plus y squared over x squared. And that's my matrix. Maybe I can redraw that bracket there. And it looks a bit of a mess. Well, it is what it is. Let's see if I can... Well, I'm going to do two things. I'm going to simplify it algebraically, but I'm also going to try and simplify it notationally as well, or conceptually, and just write that x over r, this is y over r, of course, minus y over x squared, so that's multiply top and bottom bounds, that's minus y over x squared plus y squared, and of course this will multiply top and bottom by x squared, we've got x over x squared plus y squared. And of course this is a little bit of a hybrid because I've got x's and r's on both sides, but well, we'll see when we actually have to do this, because some of the equations we're going to deal with don't have nice inverses, so sometimes we're forced to use this, and that's minus y over r times r to minus 1, and that's x over r times r minus 1. And if we go back to our little diagram here, that's r, that's x, that's y, that's a right angle, that's theta. We can write it out in this form: x over r, y over r, minus, y over r, that's sine theta, isn't it? So it's minus sine theta over r, and this one, of course, is cos theta over r. So we've got this peculiar hybrid. I guess we could carry on fooling around with it in different ways. We can eliminate that x. Of course, x is just r cos theta. So that's cos theta sine theta minus sine theta over r cos theta over r. So we can play jolly games. The reason I'm doing it is just to show you that the Jacobian doesn't have to be expressed in terms just on the left or the right hand side of your equation. You can mix and match them just to make them look simple. And I submit that this is a lot easier to deal with if you had access to r and theta than this thing here, which is a bit of a mess. That's 7 minutes. I'm going to stop there and I'm going to carry this on afterwards. So I'm going to stop there. That's Jacobian part 1, I guess.